All right, guys. Everybody have a note sheet. All right, guys. So luckily, there is no homework at this point because 6.1 through 6.5, not including 6.4, because we finished that. We tested over that. So what we're doing today is continuing on with 6.6. So if you've noticed, for the most part, we've talked about properties of exponentials and logarithmic functions. We've done evaluating. We've done everything except for solving. Solving is the only other part of exponentials and logarithms that we have left. That's the only thing we have left to do. Now we're going to do it in 4 main parts, because there's going to be these here, which we're going to talk about today, which fall under what I call one-to-one property. And we'll talk about that, or the property of equality for exponential equations. Then we'll do some with solving where it's not one-to-one, where the bases aren't the same. Then we'll do some inequalities and some other types of functions. But this here, what we're starting with, is the property of equality for exponential equations. And we do have that property there. It is in your note sheets. If b is a positive real number other than 1, then b of x equals b of y if and only if x is equal to y. And what that is saying is if the bases are the same. If we have an equation and we have one base on either side, and both of the bases are the exact same, well, the only way that this can be equal is if their exponents, the 3x, 3 minus 2x, and negative x, are also equal. So the only way this is true is if our 3 minus 2x is equal to negative x. If we have an equation where we have one base on either side, and those bases are the same, then the exponents have to be also. The only way 5 to the 3 minus 2x will be the same as 5 to the negative x is if 3 minus 2x is equal to negative x. Questions on this here? Solve for x. So there's many different steps we can do first. But the first thing I would do is add 2x to both sides. Because if we look at both sides of the equation, one has 3 minus 2x, a number and the variable. The other side is just the variable. Might as well move the variable over so they're on the same side. Because our 3 minus 2x plus 2x is just going to become 3. Negative x plus 2x is x. Well, x is indeed by itself, so x is equal to 3. Questions on this here? So here, our negative 2x plus x is 0. They cancel out. Well, negative x plus 2x, or 2x minus x, or 2 minus 1 is 1, so we just have x. Yeah, which would be 1. Yes, we could plug it into the calculator as negative 1 plus 2 to get there. Now, if we want to check and make sure this is true, we could plug back in 3 for x and see what this is. Now, we could do this in the calculator and do 5 to the 3 minus 2 times 3. And we'll see what we get. So here we could say 5 to the 3 minus 2 times 3. And the other one is 5 to the negative 3. They do both give us the same value of 1 over 125. So x is indeed equal to 3. Questions on this here? Let's look at the next one. 6 to the negative 2a is equal to 6 to the 2 minus 3a. We do have one base on either side, and they are both the same. So for this to be true, we're saying that negative 2a has to equal 2 minus 3a. The exponents have to be the same. If the bases are the same, then the exponents have to be the same also. Solve for a. What can we do first? We can add 3a to both sides. Now when we add 3a to the right side, the negative 3a plus 3a simplifies out, leaving us with 2. And negative 2a plus 3a is a. So a is 2. On some of them, I mean, we could have to do more than that, but that's, in a nutshell, it there. Questions on any of these here so far? Number 4. 3 to the 2a is equal to 3 to the negative a. Since the bases are the same, the exponents have to be the same also. So we're saying that 2a has to equal negative a. What can we do first? We can add a to both sides, yes. We could add a, we could have subtracted 2a. Adding a will tell us that 3a equals 0. If we had subtracted 2a, it would have told us that negative 3a equals 0. What do we need to do next? Divide by 3. So a is equal to 0. And that's it. And for the most part, they're keeping these pretty simple. Any questions on any of these so far? And again, at this point, if we wanted to make sure that answer was correct, we could plug it back in and verify that that is true. And if we did plug it back in, we would just get that 1 is equal to 1. Questions on any of these three so far? We're ready to look at the next one. 2 to the 2x plus 2 is equal to 2 to the 3x. Since the bases are the same, and we have one of each on either side, then the exponents have to be the same also. So our 2x plus 2 has to equal 3x. That's the first thing we can do. We can subtract 2x. And if we subtract 2x, well, our 2x plus 2 becomes 2. Our 3x minus 2x becomes x. X is equal to 2 and we're done. I mean, it could be that we have to do a few more steps, but really, that's it. Questions on these so far? We're good with these here, yes? Let's look at the next one. So we do have exponentials, yes, and the bases are the same. We have one base on either side. On the right-hand side, we do, yes. We have 6 by itself, it's one base. But the other side, we have 2, yes? If we multiply like bases, we do what? We add the exponents. So really, even though we have 6 to the 3m times 6 to the negative m, this is the same as 6 to the 3m plus negative m. Because if we have like bases, we can add the exponents. When we multiply like bases, we add the exponents. So really, our 3m plus negative m is just 6 to the 2m. If we have like bases, being multiplied together, we can add the exponent. So really, what we're doing here and what we want to try to do is get the bases to be the same and get one of them. So if it's two like bases being multiplied together, we just add the exponents. Because now we have 6 to the 2m is equal to 6 to the negative 2m. Since the bases are the same, the exponents have to be the same as well. Which means for us, that 2m is equal to negative 2m. Does anybody have a guess at what m is going to be? Yeah. It's the only way we can multiply by something. But if we want to show it, well, we can add the 2m to both sides, which will tell us that 4m is equal to 0. Questions? Questions on this here? We feel good with this so far? Now at this point, there's two different ways we can go from this. One is we just divide both sides by 4 and solve for m, yes? Zero product property states what? If I have two or more things multiplied together to equal 0, one of them must be by 4 times m, yes? So m has to be 0. Or if we divide both sides by 4, m is equal to 0. Both ways work. Questions on this here? Well, 13, we can see that we do have 4 and 4, yes? So that's not too bad, because we can jump right in this and say that that's 4 to the negative 2x plus x, yes? Is equal to 64. And since the bases are the same, the exponents would be also, yes? But the bases aren't the same, right? Because if we can make the two bases be the same, the exponents would be also, yes? So is there a way to rewrite 64 as 4 to a power? Because 4 squared, 4 times 4 is 16. If we multiply it by 4 again, we get, so that'd be 4 to what power? Cubed. 4 to the third power is 64, yes? So what we could say is that 64 is actually 4 to the third. Because if we can rewrite a number, so here 64, we didn't have that on the previous ones. But if I can change it to a number to a power, here we want 4 because the other side's base is 4. Because if the bases are the same, the exponents have to be also. So if we can rewrite it as 4 to a power, that helps us. Because 64 is now 4 to the third. Our other side, negative 2x plus x is, well, negative x, yes? So we're now saying 4 to the negative x is equal to 4 to the third. Now the bases are the same, yes? And if the bases are the same, the exponents have to be the same also. So we're saying that negative x is equal to 3. Yes. Now we can multiply by negative 1. We can divide by negative 1. But it's really going to tell us that x is negative 3. So what we're saying is that 4 to the negative 2 times negative 3 times 4 to the negative 3 should give us 64. 4 to the negative 2 times negative 3 times 4 to the negative 3 is indeed 64. Questions on these so far? Now, did we have to use 4? No. I mean, we could have rewritten this as 2, because 4 to the third is 64. 2 to the sixth is also 64. It would have given us the same answer, but our 4 to the negative x we would have to rewrite as a base of 2. So there's sometimes we can go smaller with our base. It will get us to the same answer. It just means that this equation is going to be a little bit bigger, because it would have told us that negative 2x is equal to 6, which still is x is equal to negative 3. Questions on this here? We're ready to take this a step further. (100 to the x is equal to 1 over 10 to the x minus 3. Well, we want these to be the same, yes? Well, out of both of them, 1 over 10, we can make that a little bit nicer, because it is possible to move that 10 from the bottom of the fraction to the top. Because if we do that, fraction simplified, because we just moved it up. The only thing left in the bottom of that fraction is 1. But in order to do that, we have to make its exponent negative. If I move that 10 up, the exponent becomes negative. And since the only exponent with the 10 was 1, since there wasn't one written, it's just 10 to the negative 1. Questions on this here? Well, the other side is 100, yes? Can I rewrite that as 10 to a power? 10 to the second. So what we're saying over here is we have 10 to the second power, 10 squared to the x. Yes? Questions on this here? Powers of powers multiply. Powers of powers multiply. So our 10 squared to the x is the same as 10 to the 2x. Here, we're multiplying our negative 1 and x minus 3. Well, negative 1 times x is negative x. Negative 1 times negative 3 is plus 3. So here we had to get the bases to be the same. And we were able to do that, which is just telling us that 10 to the 2x is equal to 10 to the negative x plus 3. So was this significantly harder than the previous ones? No. The only real challenge to this here is getting those bases to be the same, because once we get them to be the same, the exponents have to be the same as well, which means 2x is equal to negative x plus 3. So our first step would be to add x to both sides. So 3x equals 3. So x is equal to 1, because at this point, first time we actually had to do something after our first step. We divide by 3 to get x by itself, and so x is equal to 1. And the nice thing with these exponentials is that any value of x, we don't have any restrictions. We don't have extraneous solutions on these here. The only time we will is if x works out to be I, our imaginary numbers, then that doesn't work. But we don't have any other restrictions to worry about. Questions about this here? Let's look at the next one. 81 to the x is equal to 1/9 to the x plus 3. Yes. So our 1/9, well, it'd be nice if we can get it back in the numerator. So we move the 9 to the top, and it's going to be to the negative 1. Now, we didn't necessarily have to do it. It's a little bit easier, because the other option is to turn 81 to the 1/9. That's not as nice of an option. It's easier just to move the 1 to the top. And 81 is 9 squared, because 9 squared would be 81. Now we could again, like the previous one was 64, we could have taken this to 3. Because 3 squared is 9, we can get both of them in terms of 3. But this here's a little bit nicer. If we see this first, let's go with it. Now we can simplify our exponents a little bit, because powers and powers multiply. So we'd have 9 to the 2x is equal to 9 negative x minus 3, yes. Yep. I was just going off the previous one. And if the exponents, or the bases are the same, the exponents have to be the same as well. So here we can add x to both sides, telling us 3x is indeed equal to negative 3. Divide both sides by 3. So x is equal to negative 1. Questions on this here? Questions on any of this so far? We're ready for one more before we move to the one-to-one property with logarithms. Solve each equation. 3 to the 1 minus 2x is equal to 243. Now 3 on our one side, well, 3 is prime. So there's no way for me to rewrite 3 as a number to a power. That's as simplified as it gets. Now that gives us a kind of hint that hopefully we'll be able to rewrite 243 as 3 to an exponent. Take a guess. Fifth is indeed 243. So that means the other side is just 3 to the 5th. Because with these here, we really want the bases to be the same. Because if the bases are the same, the exponents have to be the same as well. What can we do first? We can subtract 1. Because up to this point, we've been moving x first. But here, the variables, x, is already by itself. It's on one side. So let's move the numbers to the other side. And it'll tell us that negative 2x is equal to 4. Divide both sides by negative 2, telling us x is negative 2. And that's it. Questions on this here? Are you ready for the last piece of 661? Property of equality for logarithms. I still like calling this the one-to-one property. If b, x, and y are positive real numbers with b different from 1, base can't be 1, log base b of x is equal to log base b of y if and only if x is equal to y. Pretty much our exponential property. I did add in that that x and y can also not be 0, because what's inside the log cannot be 0 or negative. And it's not that x cannot be 0. Like if we look at this first one here, 4x minus 7, that value cannot be 0 or negative, because we can't have a negative number or 0 inside of a log. But for this here, the natural log of 4x minus 7 is equal to the natural log of x plus 5. Okay? Do we have one log on either side of the equation? Is it the same log? Both ln, yes? So since I have one log on either side and they're the same log. It means that what's inside of each of these has to be the same. Since ln of x is equal to ln of y, x has to equal y. Since they are the same log, what's inside of them must be the same. Solve for x. We can what? We can add 7. Because our negative 7 plus 7 would be 0, telling us 4x is equal to x plus 5. Then we can subtract x from both sides. Because 3x is equal to divide both sides by 3. That's it. We can plug it in and check, but here we don't have to. It will work that both sides are the same. Questions on this here? What is the base with ln? Not 10, it is e. log would be 10, yes. Now, this is above and beyond. But e, if I put ln of 4x minus 7 to the base of e, the e at ln would do what? Cancel, yes. But if I do it to one side, I have to do it to the, well, both of those are canceled, telling us 4x minus 7 is equal to x plus 5. You know, so that's the reason that works. Is we could put both sides of the base of e and the ln cancel on both, giving us that there. The same thing's true for this here. ln of 7x minus 4 is equal to ln of 2x plus 11. Since they're both the same log, and we have one of them on either side, we get 7x minus 4 is equal to 2x plus 11. So 7x minus 15 is equal to 2x. Minus the 7x from both sides. Minus negative 15 is equal to negative 5x. Divide by negative 5. Telling us x is equal to 3. Questions? That's fine. We feel good with this here. Solve natural log of 5x plus 2 equals natural log of x plus 10. Well, all this is saying is that 5x plus 2 is equal to x plus 10. Since the logs are the same and there's only one of them on either side, what's inside of them must be the same. Let's see. Well, I'm going to subtract 2 from both sides. Telling us 5x is equal to x plus 8. And we can also subtract x. Telling us 4x is equal to 8. Lastly, we would divide by 4, telling us x is equal to, because 8 divided by 4 would be 2. So yes, it was indeed 2. Questions on this here? Now, it's not written, but there are parentheses technically around the 5x. 5x is still contained inside the log. And even though it's not ln, our natural log, it's log, we still have one log on either side of the equal sign. They are indeed the same log. So all this is saying that 5x is equal to 2x plus 9. So again, just like the previous ones, we are solving for x. Subtract 2x, 3x equals 9. Divide by 3. Questions on these here? I mean, if we wanted to check this here, log of 5x equals log of 2x plus 9, well, you can say log of 5 times 3 and get this here. Then we can say log of 2 times 5, what is it, plus 3? I'm trying to, 2x plus 9. So it should be 2 times 5 plus 9 is this here. Make sure. 5 times 3, 2 times 3 plus 9. That's why. I was wondering why that didn't. So we get this here, and then I'll type log of 5 times 3. That's where I got myself mixed up. And it is indeed the exact same value. Got you a little worried there for a second, yes? Yeah, but it works out to be the same. And even though it's a decimal, they are indeed the exact same decimal. Questions on this here? We can look at 11 and 12. It's the same thing. It looks different. V squared plus 35, log base 12 of v squared plus 35 is equal to log base 12 of negative 12v minus 1. Are the logs the same? If the logs are the same, then what's inside the logs must be equal. Because the only way that these are equal, and they're both the same log base, then what's inside must be equal as well. Now, the only main difference between this and what we've done previous,
it's the same, or is it just
x? Is x instead of v. That's fine. I will fix that. Yeah. It will work out the same way. I like x a little more than v, because we're more used to that. So the questions on this so far. Now, since it's a quadratic, we do have an x squared term, v squared term. We have to get this equal to 0. So we could do that. I normally tend to move everything towards the x squared. Add 12x, because I want to keep that x squared, that quadratic term, positive if I can. X squared plus 12x plus 36 is equal to 0. Questions on how we got to this here? We can graph it, we can factor it, quadratic formula, completing the square, any of these work. Now, graphing might work out nicely because the term in front of x squared, our a value is 1, so the likelihood to have fractional answers is very little. If we factored this, third term's positive, so the signs are the same and match the sign in the middle term, plus and plus. Factors of x squared are x and x. And we do have 1 and 36, 2 and 18, 4 and 9, 6 and 6. So 6 and 6 is what we want, because 4 and 9 would give us 13. Zero product property states that if we have 2 or more things multiplied together to equal 0, one of them must be 0. And if we graphed it, it would give us the single point negative 6. Because when we graph it on the table, negative 6 gives us a y value of 0, and that's our solution. We have 2 of them, but they're both the same point. And for all the ones we will do at this point, we won't have any restrictions. Questions on this here? I think we feel comfortable with these, yes? Homework on page 341 is 5 through 8, 11, 12, 21 through 24. Yep. And luckily for us at this point, we don't have any that are like 11 or 12. I just wanted to throw that in there so we see it. So 5, 6, 7, 8 are what we started out with. 11 and 12 are the same thing, but we just got to get the bases to be the same. Because 5, 12, I believe we can actually rewrite as 8 to a power, or 2, it's up to y'all. 21 through 24, the logs are the same, so set what's inside equal.